Okay, so first of all, let's talk about what organic chemistry is. The name comes from the fact that early on in chemistry, they identified certain compounds from living organisms, okay, organic, because they were isolated from organized, also known as living systems, all right? So those kind of compounds were categorized as organic compounds. And then everything else, things that were isolated and studied from things like rocks, the atmosphere, other sources were labeled as inorganic. But even though we stuck with the name, organic compounds today are not just those that come from living organisms, but we define organic compounds as those that are primarily carbon containing. Okay, so organic chemistry is the study of carbon containing compounds, and inorganic chemistry by default is just the study of everything else. So all the other elements of the periodic table are the focus of inorganic chemistry. But in this unit and in the next few units, we'll focus primarily on organic compounds, that is, compounds that are based on carbon. All right, so there are many different types of organic compounds, and so we're going to break them down into categories. And the first category to describe are hydrocarbons. Now, the name kind of gives it away, I think. You have hydro, which sounds a lot like hydrogen, right? And then carbons. So you think about this, it's kind of like hydrogen. Oh, my penmanship is really bad today. And then carbons, right? And so that's what hydrocarbons are. Those are compounds made up of only carbon and hydrogen. And another category of that we're going to break these down into, you'll see that even the hydrocarbons we're going to break down into several categories. And so the first category of hydrocarbons that we'll discuss with depth is that it's called the alkanes, okay? So these are hydrocarbons with only carbon-carbon single bonds. That's the key. They have only single bonds. Another way of putting that is that they are saturated. And you know, for example, when you say the ground is saturated, it can't take any more water. The water's just going to run off. Well, the same thing is true with alkanes. You can't add any more elements or any more atoms to them. They are saturated. That's what we mean by that. And that becomes a little bit more evident when we talk about the next category of hydrocarbons, alkenes. But know that that goes together. Alkanes, saturated, they go together. Alkanes are saturated hydrocarbons. They can't add any more atoms to their structure. Here's some examples of alkanes: methane, ethane, and propane. So you can see that the name changes based on the number of carbons that are present. So methane, those are carbon, or pardon me, that's an alkane with one carbon. Ethane has two carbons, and then propane has three carbons. And you're going to see that that's the theme here, is that we name these compounds based on the number of carbons that they have. Well, let's review something that we went over back in Unit 1, and that is VS-EPR theory, so valence shell electron pair repulsion theory. And remember that when it comes to these compounds, we can determine the steric number, and that's just the number of atoms that are bound to the central atom. So let's just say this is my central atom. It's connected to 1, 2, 3, 4. So the steric number is 4, and that is something you memorize. The electron pair geometry is tetrahedral. And even with this, let's say that we're looking at this carbon right here. What would its steric number be? It would be 1, 2, 3, 4. Okay, and that is true for all of the carbons in alkanes. Their steric number is 4, and so they are all tetrahedral. And that has consequences to it because it shows you that the structures that we draw, like you see down here, down here, these are really just oversimplifications. They exist with bond angles of 109.5, okay, in and out of the screen. So a homologous series is one that is different by only a CH2 group. So imagine if I had propane and I inserted a CH2 right there, then I would get butane. And if I did the same thing to butane, then I would get pentane. If I did the same thing to pentane, I would get hexane. So what that leads us to is a general formula for alkanes. That is C with the subscript N, that of course indicates the number of carbons, and H with the subscript has a formula of 2N plus 2. So twice as many hydrogens as carbons plus 2. Okay? So you can see that from any, pick one of these structures. Let's look at pentane. And so in this case, I've got, for every carbon, I've got 2 hydrogens, right? So that's why the relationship, you have N and 2N. And then you go through that, but then you've also got these two hydrogens on the very end, and that's what the +2 is for. Okay, so to answer this question, what is the formula for an alkane with 8 carbons? Okay, so if there's 8 carbons, C subscript 8, I know that much, but then the H is going to be 2 times 8 plus 2, so that results in a carbon with subscript 8 and an 8 with the subscript 18, because 2 times 8 is 16 plus 2 is 18. All right, now, so far we've just been drawing these hydrocarbons, these alkanes, in a straight line, as you can see here with pentane. All of the carbons form a line, but it doesn't have to be that way. You can have this formula, C5H12, and have the carbons connected in a few different ways. They can be connected in a straight chain like this. Okay, so that's what we would call a straight chain. But they can also have branches. Okay, like this would be a branch, and here this is like 2 branches. Okay, but if you were to see, or determine the molecular formula for all 3 of these, it's C5H12 for each of them. That does not change. It's just the way in which the atoms are connected. So straight chain versus some degree of branching. And we've already talked about this a little bit back in Unit 3 when we talked about intermolecular forces. Remember the analogy that I give in that lesson of the lasagna noodles versus the billiard balls, right? So if you have a straight chain molecule like this, then those London dispersion forces can be exerted on another. If I have another molecule of pentane down here, I won't draw the hydrogens just to keep it a little bit clearer, then those London dispersion forces can just exert themselves pretty much across the whole molecule. So they just exert themselves all over that molecule. But if you have these branches on the molecules, then the London dispersion forces they're interrupted, they're disrupted, they get in the way, these branches get in the way. And so the magnitude of intermolecular forces goes down when you have branching. And that also is evident in certain physical properties, as we also talked about back in Unit 3. Okay, so for example, boiling points. The greater the intermolecular forces, the higher the boiling points. And as I just talked about, these pentane molecules that are in a straight chain have more opportunities for the London dispersion forces to exert themselves compared to the isopentane, which has 1 branch, or the neopentane, which has 2 branches. Okay, let me point that out just a little bit more explicitly. So, if I popped off this hydrogen and moved this methyl group there, okay, and then reattach the hydrogen right there, then you would get this isopentane. And if you did it twice, then you would get the neopentane. And so that affects the amount of intermolecular forces, which affects the physical properties like boiling point. So the boiling point of neopentane, notice, is much lower than the boiling point when there is no branching. Up to this point, whenever we drew the Lewis structures, we showed every atom and every bond. But when you're drawing organic compounds, there are customs or traditions or ways of drawing them that are abbreviated or simplified. And so there's a couple ways that we are going to talk about in this course, and one of them is called the condensed structural formula. And so that is where you essentially get rid of the lines. So the condensed formula show the hydrogen atoms just right next to the carbon atoms to which they are attached. So here is an example, and I like the color coding here. So the CH3, it would be written like this, just CH3, but in the Lewis structure, you would see the carbon and then 3 lines and then the hydrogens. But that is just abbreviated or condensed down to the CH3. And this green CH2 is there. This red CH2 is there. And then this, if you see a condensed structural formula with parentheses, the group that's in parentheses, it's connected to the nearest carbon atom also in the condensed formula. So parentheses in condensed structural formulas indicate that the enclosed group of atoms is attached to the adjacent carbon atoms. So that may be hard to visualize. So let's just take a look at an example here. The way you would write the condensed structural formula of isobutane, which is shown here, is notice this CH3 group right here is connected to that second carbon. Okay, so that second carbon So that's this is the first carbon. So that's the first carbon. And then this is the second carbon. So this is the second carbon. And it has a hydrogen on it. So there's that hydrogen right there. And then this methyl group, they put in parentheses. Okay. And then the next carbon also has the CH3. All right, so the next type of traditional way to draw organic compounds is with something called line angle formulas. And this is the one that you'll see most. The convention here is that any end or corner implies a carbon. So carbon atoms are implied at the corner and ends of lines. And the other trick that you have to remember is that every carbon atom is understood to be attached to enough hydrogen to give each carbon 4 bonds. Remember that carbon likes to form 4 bonds. And so if the bonds aren't explicitly shown with lines, you just assume, or it is implied, that the carbon has enough hydrogen on it to make a total of 4 bonds. Okay, so let's do a little color coding again here in an attempt to see if we can explain what's going on. So right here in red, we've got a CH3. Okay, so here's the end of a line, so that represents the carbon. And then it's got one connection to a carbon that's shown with this line. That's this line right here. Okay, but the hydrogens aren't shown, but it is implied that this carbon, because we know carbon wants 4 bonds, it is implied that it's also attached to 3 hydrogens. Okay, let me change colors and I'll talk about the next one. So this right here is this carbon right here. Okay, and you can see the 2 bonds to the other 2 carbons right there and right there. They're right here and right here. Remember, the ends of lines and corners are carbons. So there's a carbon here that it's connected to. There's the carbon there that it's connected to. But what's implied is the connections it has to 2 hydrogens. Same thing for this group right there. Carbon with 2 hydrogens connected to 2 other carbons. So that's this carbon right here. It's connected to that carbon, connected to that carbon. And it's also connected to 2 other hydrogens, which are not shown. They are implied. Okay. All right, so let me move down to the next one here to talk about it. So in this case, we have a double bond. So this carbon is right. So this is that right here. So there's that carbon right there, and it's got the double bond to a carbon over here, and a double bond, or pardon me, a single bond to the carbon on the left. But that's 3 bonds. You got 1 bond here and 2 bonds here. It's a double bond. So it needs 1 more bond to make 4, and so that is implied as a single bond to a hydrogen right there. All right, one other traditional way to represent bonds in line angle formula also takes into account the 3-dimensional arrangement. So all 3 dimensions can be represented with special lines. So those lines look like this. We have methane here as an example. So sometimes if it's drawn freehand instead of printed, instead of a dashed line, it might look like a squiggly line, something like that. The idea there is the same, that it's meant to represent a bond that's going into or the page away from you. And then if you see a solid wedge or a bold line, then that means that the bond is coming out of the page, out of the screen, toward you. And if the lines are just normal looking lines, that just means that the screen or the page contains those bonds. So you do see line angle drawings with 3 dimensions also shown with the use of these dashed lines and the bold or the wedge lines. All right, so let's just look at some more examples here. We'll kind of interpret what's going on. So we have this Lewis structure, and you can see this is the condensed way to write that. We've got a C2, so there's a C2, and then H5, because there's 1, 2, 3, 4, 5. So this C2H5 right here is this part right here. All right, and so then we've got the carbon here. Okay, so that's this carbon, and it's connected to an OH group, and so that's shown in parentheses to show that that group of atoms is connected to this adjacent carbon, and then it's also connected to a hydrogen. Okay, so that's that hydrogen right there. And then the rest of the molecule is just the CH3, which is what's shown right here. Okay, so that's right there. And then the blue, it would be that carbon, and the hydrogen is implied. You don't see the hydrogen, but it's there. And then the OH group, and then the rest of the molecule, the C2H5. Again, the hydrogens aren't shown, but the end of that line, the corner there, represent the 2 carbons, and beyond that connectivity, beyond the two carbons connected to each other, we just figure out, or we determine that there are 3 hydrogens on this carbon because it needs 3 hydrogens to make 4 bonds, and that there are 2 hydrogens on this carbon because it needs 2 hydrogens to make 4 bonds. 1 bond there, 1 bond there, so it needs 2 hydrogens. This carbon only has 1 bond, so it needs 3 hydrogens. So in this case, you've got your CH3 groups, CH3, CH3. Okay, so that's represented by this part of the condensed, and it's represented here. Okay, and so then the carbon right here with the hydrogen is also connected to those groups. So that's right here. Okay, and then there it is right there. That corner where those lines intersect, okay, there's a carbon there. And you know it has to have 1 hydrogen, right? Because it, according to this drawing, is just engaged in 3 bonds. 1, 2, 3. So it also needs a hydrogen, which is implied, it's not shown. Okay, then the rest of the molecule is pretty straightforward. We won't go through that. So let's talk a little bit about naming alkanes. We're going to talk about the IUPAC rules, and there are several steps to this. First of all, what you need to determine is the longest continuous carbon chain, abbreviated as LCC, longest continuous carbon chain. And then you're going to use a word stem from that number of carbons, and we're going to put the suffix ane on it to use as the base name. Okay, so this table shows us the word stem for each number of carbons. 1 is meth, 2 is eth, 3 is prop, 4 is bute, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. So let's do some examples. So if you just have 1 carbon, then we use the stem, which is meth, and I just put the suffix ane on it, and you have the name methane. Let's do one with 5 carbons. So here is the chemical formula. Here is somewhat, it's like the condensed structural formula, although they did put some lines in there. And then the line angle formula. So we got 5 carbons, so we go to the table and we see that that is pent. All right, and then I just put the suffix ane on it, so it becomes pentane. Sometimes these structures have branches on them, and we have a special name for those. We call them substituents. The idea is that a hydrogen has been substituted with something else. So it's called a substituent. So now let's talk about how to change the name to adapt to situations like this. If the substituent is another carbon-containing group, another alkane, then you still use the word stem for the number of carbons involved, but instead of ane being the suffix, YL or IL is the suffix. So for example, and then that becomes a prefix in the overall name of the compound. So you include the substituent or substituents name or names as prefixes in the overall compound name. So here's an example. Okay, so once again, what we need to do first of all is to determine the longest continuous chain of carbons. So that would be 1, 2, 3, 4, 5. You could also count, there's 3 carbons here, a continuous chain here, 1, 2, 3, but that's not the longest continuous chain. The longest continuous chain is here, 1, 2, 3, 4, 5. Okay, so we've got 5 carbons in the longest continuous chain. So what does that tell us? Well, we go to our table, and the word stem is pent. Okay. But one of the hydrogens on this alkane with 5 carbons has been substituted with this group right here. Okay. And that is a 1 carbon substituent. And so the word stem for 1 carbon is meth. And then as it says up here, the suffix is going to be YL because it's a substituent. And so this is going to be the prefix, and then pentane is going to be the base name. So this compound I would call methyl pentane. Okay, but we're not done. If you notice that this CH3 group it was on this carbon right here, but it could have been on this carbon. It could have been on this carbon. So how do you distinguish, or how do you represent in the name which carbon it really is on? Well, we do that with numbers. And so that is step 3. So we include numbers in the substituent prefix to indicate on which carbon in the base chain it is attached. All right, so one other rule to keep in mind when applying these numbers is that you want to have the lowest numbers possible in the name. And then the convention is to separate the numbers from words with a dash. Let's say that this is our carbon number 1. So this would be carbon number 2. This would be carbon number 3. This would be 4. This would be 5. That gives us the lowest number possible, which is what we're shooting for right here, right? Because that would put this substituent on the second carbon. Let me erase and show you how we would get the number if we went the other direction with numbering. Okay, so if I called this carbon 1, and this was carbon 2, this was carbon 3, this was carbon 4, and this was carbon 5, then the substituent would be on the fourth carbon, which is not the lowest number possible. So the reason why I number in this case from left to right is because that puts the substituent on the nearest carbon, so it would have the lowest substituent number. 2-methyl pentane is the correct name for this compound. And again, notice the dash just separates the numbers from the words. So far, we've just talked about situations where there's just one substituent, but there are many, many situations where you have multiple substituents. And so in that case, what you do is you name them in alphabetical order. Okay, that's one important thing. And if you have multiple of a single type of substituent, then you're going to throw another prefix into the mix, the Greek prefixes, to designate the number of that substituent type. Okay, so for example, if there's 2 substituents that are identical, that would be di. There's 3, there's tri. If there's 4, there's tetra, and so on. And the other important thing to remember is that those prefixes are not what determine how the name gets alphabetized. Because remember up here, we said that if there are multiple substituents, we put them in alphabetical order in the overall name for the compound. But it's the actual substituent's name that determines the alphabetical order, not the numeric prefix that might be tacked on in front. Okay, so for example, ethyl, that's where you have 2 carbon in the substituent. So it would be C, H, H, and then another C, and then 3 hydrogens. Okay, so this is the substituent ethyl, and it comes before methyl or dimethyl because E, comes before M. That's the alphabet. That's how you alphabetize it. You compare the first letter of this substituent with the first letter of the methyl substituent. Methyl, of course, is that's a carbon with 3 hydrogens. But what this name is implying is that there's 2 of them. So somewhere in the molecule, there's 2 methyl substituents. But if there was also an ethyl substituent in the name, it would come first because of the alphabetical order. And then the other little convention that we follow is that the last substituent is just used as a prefix and is put together with the root name, the stem word, to form one word. So the last alkyl group is prefixed to the name of the parent alkane to form one word. Okay, so these are a lot of rules, a lot of words on a page that may not make a lot of sense, but we'll do some examples to hopefully help clarify. Okay, so here's some examples. And with these first 2, we're just going to see how the name makes sense when you look at the structure. And then we'll actually come up with a name for this one over here. So first of all, the longest continuous carbon chain. So I've got 1, 2, 3, 4. Or if I go this way, I've got 1, 2, 3. Or if I go this way, I've got 1, 2, 3. So the longest continuous carbon chain is this one forming a horizontal line right there. So we got 1, 2, 3, 4. So that's where we get the butane as the base of the name. And then on this butane, there are 2 CH3 groups acting as substituents. So that's where we get the methyl, because if it's one carbon, that's methyl. And then there's 2 of them, so it's di, so dimethyl. And they are both on carbon 2. That's where we get the 2, 2. You see the comma there shows that they are both substituents, and they're both, in this case, on the second carbon. Now distinguish that between this one. So it's still butane, 1, 2, 3, 4. That's the longest carbon chain. There's still two methyl substituents, dimethyl. But now, if this is carbon 1, 2, 3, 4, one of the methyl substituents is on carbon 2, and the other methyl substituent is in carbon 3. So you can see the need for the comma there to designate which carbon the substituent is on. Okay, so now let's talk about this one. So first of all, let's identify the longest continuous carbon chain. So there's 3 right here, 1, 2, 3. There's 1, 2, 3, 4, 5 there. 1, 2, 3, 4, 5 there. And so since that goes in a straight line, let's consider this to be the backbone of our compound. And so that's 5 carbons. Okay, so the word stem is pent, right? And so if I just throw the suffix ane on there, so this is going to be some form of pentane. So I know I'm going to be putting some prefixes on it, so let me rewrite that down here. So pentane, I'm going to be putting some prefixes in front of that. Okay, so there's 2 different substituents here. I've got a 1 carbon substituent here, that's methyl. And I've got a 2 carbon substituent here, so that's ethyl. Okay, and so now I've got my name. I know it's going to be ethyl methyl pentane because it is alphabetized, right? E comes before M. Okay, but before I write it down here, I want to get the numbers because they're on specific carbons, and we want the lowest numbers possible. So if I make this carbon 1, and that carbon 2, and that carbon 3, this carbon 4, and this carbon 5, then the ethyl, which is going to come first, is on carbon 3. So I go 3 dash ethyl, then another dash because I got to put another number, and this other number is going to be a 2 because that's where the methyl. So and then another dash, and then methyl. Okay, and then that would just no spaces or anything. I didn't draw it quite right, but I'm going to bring up the typed out name. It looks prettier in just a second anyway. But this methyl, this last substituent name, simply becomes a prefix on the base name. So this compound, I believe, is called 3-ethyl 2-methyl pentane. All right, so now let's talk about some of the physical properties of alkanes. First of all, one important property is that they are nonpolar, and as a consequence, they are not soluble in water. So how do I know that? How do I know that all alkanes are nonpolar? Well, the only type of bonds in alkanes are carbon-carbon bonds, which have no electronegativity difference, and carbon-hydrogen bonds, which have a very small electronegativity difference. So the electronegativity of carbon is 2.5. The electronegativity of hydrogen is 2.1. So that difference is only 0.4. So it's very small. So that means that all of the bonds in alkanes are nonpolar. And you have to have polar bonds in a molecule to even possibly have a polar molecule. So I can say with confidence that all alkanes are nonpolar, and one of the consequences of that is that they are insoluble in water. Well, maybe you remember when we discussed solubility a little bit, we threw the phrase out there, like dissolves like. So we can learn from that or think from that alkanes must be soluble in each other because they're all nonpolar. So one alkane must be soluble in a different alkane, and that is true. And one word for that is miscible. Remember that the word miscible means that they will form a solution. They'll mix together uniformly in any proportions, no matter what, whether it's 1 in 10 or 50-50, it doesn't matter what the proportion, the two compounds will mix together uniformly. That's what miscible means. We talked about that when we talked about gases. Gases have that property, how they are miscible. But when it comes to alkanes, if we mix them together, they will dissolve each other. They form uniform mixtures. They are commonly used as solvents, actually, because of that property. And we use them to dissolve things that are not soluble in water. They are generally less dense than water. If you mix a liquid alkane with water, they would separate into 2 layers, and the alkane would be floating on top of the water. And the phase that they are in, generally speaking, is either the gaseous phase or the liquid phase at room temperature. Okay, and I put this picture up here because you can buy alkanes at Home Depot or lots of other places. They are often used as solvents for things that don't dissolve in water, like grease and paint, okay, varnish. Now, this is just a table to kind of demonstrate some of their physical properties, like their physical state at room temperature, how their densities are less than water. You don't need to memorize any of the numbers here, of course. It's just to give you an idea about what the physical properties are like. Okay, so now let's talk about some chemical properties of alkanes. One of them that's very common, very popular, is combustion. We use alkanes as fuels. So the general reaction is shown here, but it's written for methane, but it applies to pretty much any alkane, that if you add some energy to get the reaction started and it occurs in the presence of oxygen, you get the combustion products, carbon dioxide and water, and it is an exothermic reaction, so you also get some energy in the form of heat. Okay, another reaction that they can undergo is they can react with a halogen, but you have to have UV light present as well. So the type of light that gives you a sunburn, right? Or sanitizes things. If you work in a hospital where you sterilize things, a lot of times ultraviolet light is used to sterilize surgical instruments and packages and things like that. So if you have alkanes in the presence of a halogen like bromine, in the presence of UV light as well, then what happens is one of the hydrogens gets kicked out and forms a bond with the halogen, and then the other halogen then connects to the carbon in the alkane. But that's it. Those are the only two reactions that alkanes typically will undergo. So we do think of them as mostly inert, which means they're not reactive. And so there's a good side and a bad side to this. Let's talk about the good aspects first. So as we mentioned before, because they are relatively inert and because they are pretty good at dissolving stuff, they are used often as solvents. And we know that they're not going to interfere in the reaction because they're not very reactive. They're mostly inert. So the other situation that makes them good is when you want a barrier to keep out water, when you want a moisture barrier. So they can be used in situations where you don't want water to interfere with whatever's going on. So, for example, you're familiar with Vaseline. Vaseline is petroleum jelly. So these are just high molar mass alkanes and other, hydrocarbons. But because they don't dissolve in water, if you were to put it on a baby's bottom or under your nose, if you got a sore nose or something like that, it forms a moisture barrier. So it prevents chapping and diaper rash, things like that, due to the presence of moisture. Okay, so that's the good, but there's also some bad stuff about it. Because they're not soluble in water, it's difficult to get rid of alkanes and other hydrocarbons if they find their way to places where you don't want them. The environment, for example, oil spills, or if you were to ingest some, that's also a problem because they can interfere with biological processes that require water. And so it can be toxic if ingested, right? So the bad news for alkanes is that they are difficult to remove from the environment or the body of a living organism, and therefore can be quite toxic due to their interference with processes involving water and or oxygen. Okay, so now let's talk about halogenated alkanes or halogenated hydrocarbons, more generally speaking. And that is where, as we showed in a previous slide in one of the chemical properties, you just replace a hydrogen with a halogen. Okay, so now, first of all, let's talk about the naming rules, how that impacts those. Well, we just think of the halogen atom as a substituent, and we treat it just like we did the alkyl substituents, methyl, ethyl, and so forth. But the suffix on the halogen's name is going to be an O instead of a YL. So fluorine, you would write in the name as fluoro, chlorine, chloro, bromine, bromo, iodine, iodo. So here's some examples of compounds with a halogen as a substituent and how that affects its name. So in this case, we have methane, but one of the hydrogens has been replaced by this bromine. Okay, and so up here we learned that the name for the bromine becomes bromo. Okay, and it's going to be a prefix, just like the substituents before were prefixes. So I'm going to say this is bromomethane. Okay, the base name is just, it's one carbon, so that's where I get the methane. And then I treat the halogen like a substituent, and I change the end of it to an O, so bromomethane. All right, for this one, I have two chlorines. So I'm gonna, and again, it's one carbon, so the base is methane, but with the halogens, I've got two of them as substituents. So I'm going to use my Greek prefix to indicate the number, di, so dichloromethane. Okay, so for this one, I still have dichloro, but they're not on the same carbon. They're on different carbons. And so this has 1, 2, 3 carbons. So I remember, or I look up if you haven't got the base names memorized yet, but 3 is prop. So this is propane. Okay, and it's still dichloro. So dichloro. But I need to indicate what carbons these are on. So they're on carbon 1 and carbon 3. So I go 1, 3 dash dichloropropane. So instead of a Lewis structure, I just got the condensed structure here. So, this just gives us a little bit more practice interpreting these condensed structures here. So this bromine is on this carbon right here. So remember that the substituent is just attached to the nearest carbon. There's only one of them, and I don't need to, I guess we should say, because it could be attached somewhere in the middle, we could say that this is 1 dash bromo, and then this says 1, 2, 3, 4 carbons, so that is butane. Here, if we count carbons, we've got 1, 2, 3, or 1, 2, 3, but since this one includes the substituent, bromine, we're going to go with this is carbon 1, this is carbon 2, and this is carbon 3. It's 3 carbons either way you go. So our base name is propane. Okay, and I've got a bromo on the, oh, you know what? I need to change the numbers. This is good. So notice that I numbered it from left to right, 1, 2, 3. But remember, you always want to number it so that the substituents get the lowest numbers possible. So I'm going to go in the other direction. And I'm going to say, this is carbon 1, this is carbon 2, and this is carbon 3. Okay, because then I've got, and again, I'm going to do this by alphabetical order because this right here, that's name, its name would be methyl. Meth is the base, and because it's a substituent, I get the YL suffix. And this one is bromo, chicken scratch, pardon my penmanship. This is bromo, okay, which a B comes before M. Okay, and it's on the first one, so I'm going to go 1 dash bromo, and then on the second carbon, so dash 2 dash, and then this is called methyl propane. So 1 bromo, 2 methyl propane. So with this one, it's still bromo methyl propane because I've got a longest continuous chain of 3 carbons. I've got a bromine substituent and I've got a methyl substituent, but it's going to be numbered differently. Here, the bromine was on the first carbon and the methyl was on the second carbon. In this one, both the bromo and the methyl are on the second carbon. So I'm going to call this one 2, it's on the, right, 2 dash bromo, and then a 2 dash methyl propane. So what we've talked about so far are the IUPAC names and their rules. And we will strive to do that for the simple compounds. But what you're going to see before too long in future lessons is that there are many different types of organic compounds where the common name is used instead of the IUPAC name. Because the IUPAC name just gets, it's very informative, but it gets very complicated. So I don't expect you to be able to name everything by the IUPAC rules. What I'll be looking for is really just recognition, connecting names with formulas, names with structures, things like that. I will not ask you on a quiz or on a test, the final exam, to write out the name given the structure, or given the name, write out the formula correctly. What I would expect you to do is to match them, match the correct name with the correct formula, things like that. So what I would call recognition knowledge. All right, so halogenated hydrocarbons that we just talked about in the previous slide, they're one of those type of compounds where when they were discovered, people thought they were just the greatest thing since sliced bread. They found so many different uses for them. And they still are widely used, but it turns out that many of the uses that were employed were harmful for the environment and in terms of their toxicity. Perhaps you heard about like the hole in the ozone layer, the destruction of the ozone layer. Well, it was halogenated hydrocarbons that caused that, particularly when they were used as a propellant and aerosol, but also just due to the decomposition of plastics and other materials that were made of halogenated hydrocarbons. The halogens themselves would detach in the upper atmosphere as free radicals, which interrupts the equilibrium between oxygen gas and ozone gas. So it was causing a hole in the ozone layer, which of course is the ozone layer is what blocks a lot of the harmful UV radiation coming from the sun. So that's not good. So over time, many of the products that utilized halogenated hydrocarbons have been reformulated to not have them, or to use a halogenated hydrocarbon that does not decompose in the upper atmosphere in a harmful way. Okay, so one more type of alkane that we want to hit on in this lesson are the cycloalkanes. So they are the hydrocarbons that exist in rings, all right? So the way you name them is you just put a prefix cyclo in front of the name of the corresponding open chain alkane. So it leads us to the formula of CnH2n. So for example, if you have cyclopropane, so it's got 3 carbons in it, so prop, and it's an alkane, so propane, but the 3 carbons are connected in a ring. It looks like a triangle. So we call it cyclopropane. And if you count hydrogens here, there's 2, 4, 6. So that would be twice as many hydrogens as there are carbons. So we get the general formula of C sub n, H sub 2n. And cyclohexane, hexane, 6, cyclo meaning in a ring, so 6 carbons in a ring. And if you were to do the line angle drawing, all you'd have was the look of a hexagon. And in this case, it looks like a triangle. But we know, again, from our discussion earlier about the line angle diagrams, that at the corners, there are 2 hydrogens because these carbons also have 2 connections to other carbons. And so they've got 2 more bonds, and those are with hydrogens. All right, so their properties are just similar to those of corresponding open chain compounds. And so we'll end this lesson with just a couple examples of cycloalkanes, and in particular with substituents. Their naming rules are the same as the alkanes. So let's practice here a little bit of that. So what is the molecular formula for cyclooctane? So cyclo being ring and octane meaning 8. So that's carbon with, where there's 8. So the formula has C with a subscript of 8 because there's 8 carbons. And then I remember the formula is Cn and then H2n. So that would be C sub 8, H sub 16. Okay, and what is the name of this compound? Well, it's cyclopropane because I see the triangle there. Okay, and this has 2 carbons in it. The substituent has 2 carbons, so I know that it is ethyl. So this would just be ethyl cyclopropane. Okay. And you don't need to have numbers in this one because it would be indistinguishable if the ethyl was attached here or here. So there's no way and there's no need to employ numbers in the name.